Hi, we're going to pick up where we left off discussing the tensor product, specifically focusing in on the property called flatness. Okay, we'll start by defining flatness. Then we'll try to give a couple of perspectives on why this notion of flatness is defined, why it's justified. We'll give a perspective from linear algebra as well as from algebraic geometry. We'll start off with a description of the functor tensoring by M. Okay, so we define the ring A. So we'll let A be a ring. And we'll have M an A module. Then tensoring by M is a functor from A modules, the category of A modules, to itself. Okay, and obviously we're tensoring over A. And how does this act on objects? Obviously it takes a module n and it maps it to n tensor with M over A. As for the morphisms, so this is for objects. What it does on morphisms, well, I need to have, if I start with a map from F, F going from, let's make it N to P, this is a morphism. Okay, so obviously the map induced by the functor has to map n tensor M to n tensor, P tensor M. And the map that we're going to define to do that is F tensor 1. Okay, and the way that this will act, taking some element in the tensor product, which will be defined as ni tensor mi, where I is some finite indexing set. It's going to map this to the sum of f of ni, tensor mi. Okay, indexing over the same set. Okay, so obviously the f of ni's are all in P. So this defines a map from n tensor M to P tensor M, and we'll slip in these A marks. Okay, so as a functor, tensoring with M sends a homomorphism of A modules from N to P to a new homomorphism going from N tensor M to P tensor M. And we saw in the previous lecture that tensoring with M is right exact. So let's recall what that means. If we have the following sequence, okay, if we know this sequence is exact, meaning that the kernel of one homomorphism is the image of the previous homomorphism, then applying our tensor, our functor tensoring by M, what we'll get is a new exact sequence. Okay, and this is called right exact because we're looking at the right half of a short exact sequence. And what this is telling us is that tensoring with M preserves co-kernels. On the other hand, this functor tensoring by m is not left exact. What does that mean? That we start with a sequence, an exact sequence of this type, and let's use n's. Even if this is exact, once I apply this functor and I get n prime tensor m mapping to n tensor m mapping to n double prime tensor m, this is not necessarily exact. Okay, and a useful example here is the following. So if we have 0 maps to z, maps to z, maps to z mod 2z. Okay, so where we apply the multiplication by 2 map. Okay. So clearly this is exact, right? There you have this injective map multiplication by 2. The only element mapping to 0 is 0. And then when you quotient by the image of that, you get z mod 2z. Okay, so this is an exact sequence. And yet, when I apply the tensor with the z module z mod 2z, okay, we're tensoring over z, what we get is z tensor over itself with z mod 2z is z mod 2z. The multiplication by 2 map, okay, when you pair it with the identity map on z mod 2z, this becomes the 0 map. Okay. And that gets mapped to z mod 2z again. And then we get the tensor product of z mod 2z with itself over z. Okay. But the key here is that this map is not injective. This is not injective. And so the sequence is not exact. Okay, so this tells us that we shouldn't be hopeful for any module to lead to an exact functor. But what if we knew which types of modules did lead to exact functors? Okay, and that's exactly what flatness comes to answer. A module is called flat if any of the following equivalent conditions are satisfied. So we can express this condition in terms of the tensor inducing an exact functor, as we stated. We can reduce that instead of being an exact functor, so it preserves long exact sequences. It's enough that it preserves short exact sequences. It's also enough if the tensor functor takes injective morphisms to injective morphisms. And it's even enough just to do that for finitely generated modules. Okay, so let's go through some of these equivalences. So first off, the equivalence of 1 and 2. Okay, so 1 implies 2. That's trivial because if it's true for any exact sequence, it's certainly true for short exact sequences. Okay, so this is trivial. Or 2 implies 1. You would take your long exact sequence, A to B to C to D to E, etc. And let's name these maps: alpha, beta, gamma, delta, epsilon, etc. You could break this down into short exact sequences as 0 to A to B to image of beta, and then since that's surjective, it go to 0, and then you pick up with the co-kernel of alpha, map that into C, which then maps into the image of gamma, maps to 0. And you would continue from there. If you can show that the exactness is preserved on all of these smaller short exact sequences, that implies exactness of the that implies that exactness is preserved when you apply it to the long exact sequence. Okay, well, let's go from 2 to 3. This follows straightforwardly from the fact that n prime to n is part of a short exact sequence. Okay, so if this is injective, okay, so then once you tensor, that's going to preserve the exactness. Okay, going the other way, 3 to 2, so it's basically combination of the injectivity with the fact that, so injectivity means that you're preserving kernels, and we know that tensoring with M always preserves co-kernels. So once I'm preserving kernels and co-kernels, I know that the short exact sequence gets preserved. Okay. And let's just show the equivalence of 3 and 4. So 3 implies 4 is obviously trivial, since if it's true for general modules, then it will be true for finitely generated modules. Going from 4 to 3 is a little trickier. And the idea here is to start from general modules and restrict your attention to the submodules where you would have, you would find the finitely generated submodules where you would find elements of the kernel. Okay, so for example, okay, so we want to prove 3. So take an element in the kernel of f tensor 1. Okay, so let's let x, so it's going to be of the form x tensor xi tensor yi, where I is in some finite index set. And so this is going to be in the kernel of f tensor 1. Being in the kernel of f tensor 1 means that the sum of f of xi tensor yi as an element of this new module, or the target module n tensor m, is going to be equal to 0. Okay. So we can define n0 prime to be the module generated by the xi in this case. Okay, and then we can also find a finitely generated submodule of n. Okay, so n0 is a finitely generated submodule of M containing f of n0 prime. Okay. Once you make these definitions, you find that we have f tensor 1 applied to this element xi tensor yi in n0 prime, a finitely generated module, mapping to another finitely generated module, is equal to 0. So that must mean that this sum in itself was 0. So that means in turn that f tensor 1 is injective for general modules. We're implicitly using that every element of a tensor product is a finite sum of tensor product of elements of the constituent modules, which allows us to focus on a finitely generated submodule. Let's get this a little more room to breathe. Oh, shoot. Okay. Okay, so now we can move on to discussing why flatness is a useful property and how it shows up, how we can interpret it through analogies to other areas of math. And one such area is linear algebra. So let's think about linear dependency and how it relates to bases of a vector space. So let's say I give you some collection of vectors, v1 through vn, and I tell you these are elements of a vector space V. And furthermore, they're linearly dependent. Okay, so there exists a collection of, let's call this a K vector space. There exists a collection of elements A1 through AN in K such that the sum of AI VI, where I goes from 1 to n, is equal to 0. Okay, well, what that tells me is that the original set of vectors I chose were linearly dependent in the start. But if I wanted to translate to a basis, so suppose we can take a basis W1 through WM so that VI can be written as the sum of Bij Wj, where j goes from 1 to m. Then what happens when I rewrite this equation in terms of the basis elements? The sum of I equals 1 to n of AI Vi, this becomes a double sum of AI Bij, where j goes from 1 to m, I goes from 1 to n with Wj. Okay, and we can switch the order of summation so that we're looking at j equals 1 to m, I equals 1 to n, AI Bij, Wj. And what we know about linear independence, given that Wj is a basis, I learned that all of these coefficients, these summations over I, all of those must be 0. Okay. In other words, when we have some collection of elements that cancel to 0, we can trace this to cancellation in the coefficients once we get a nice representative collection of elements like the elements of a basis. Okay, so once I know I'm translating to a basis, I can rest assured that all of the cancellation is happening in each of the coefficients. How do we translate this to the context of rings and modules? Okay, so suppose we have a collection of elements of our module. Okay. And let's say there exists A1 through AN elements of the ring A, such that our sum AIXI is going to be 0. Then the module is considered to be flat if there exists a collection of elements y1 through ym such that xi can be written as the sum of bij, yj, j equals 1 to m, and the sum of, basically the same thing happens as with vector spaces. So if we try to translate this AIXI into this double sum, let's first sum over the j's, and then we'll sum over the i's. Okay, so this will be 0, and that will imply in turn that the sum of ai, bi, j, where j goes from, where I goes from 1 to n, is also 0 for all I. Okay, so it's saying the same phenomenon happens here with modules as with vector spaces. The relaxation that we have to do is that we don't have bases in modules the way that we have them in vector spaces, but we need to be able to select a basis-like collection of elements to resolve these xi's into smaller pieces so that the coefficients again become the problem. So that as is described in the NLab account that this is based on, nothing happens in the module except as a result of things that are happening in the ring of coefficients. Okay, so that's a linear algebra perspective on what flatness can do. And so the fact that this is equivalent to the tensor product being exact as a functor is a more complicated proof, but I invite you to look into that in the NLab page on flat modules. Okay, and let's state this explicitly. A module M is flat if and only if for every finite linear combination where the sum of AIMI is equal to 0 in the module M, there are elements nj and linear combinations mi equals sum of bij nj, where bij are elements of the ring, such that for all j, the coefficients are 0. Okay. Now we'll explore the algebraic geometric perspective on why flatness is important. And to do that, we have to start by defining an affine algebraic variety. And this approach is based on chapter 6 of Eisenbud's commutative algebra. I believe the topic of the chapter is flat families. Okay, but let's start with algebraic varieties. So we have K a field, and we're going to let I be an ideal in polynomial ring with coefficients in K. Okay, so given this ideal, the set of points V inside of n-dimensional space over K, for which all polynomials in I vanish, is called an affine algebraic variety. The affine coordinate ring which can be thought of as the set of polynomial functions in terms of their values on the set V. Okay, this is the polynomial ring modulo the ideal I. Okay, since all of the polynomial functions in I vanish on V, if I'm only interested in the values of my polynomial functions on V, then adding or subtracting anything in I doesn't affect the values of the polynomial functions there. So for that reason, this can be considered the ring of algebraic functions on my variety. Let's do a quick example of this. So let's consider K. Let's let K be the field of real numbers, and we'll look at the multiples of y minus x squared inside the ring of polynomials in x and y. Okay, then the corresponding variety V is simply let's do this in red, the parabola where y is equal to x squared, because that's exactly where those polynomials will be equal to 0. And I forgot to mention, this is called A of V. So in our case, A of V will be equal to the ring of polynomials R adjoin xy modulo y minus x squared. Okay, but if you'll notice, y minus x squared, that just means that whenever I am interested in writing down y, instead I could just as easily write x squared. So this is isomorphic to R adjoin x. So what is a morphism of varieties? Let's say you have x inside of Kn and y inside of Km, and they're both algebraic varieties, affine algebraic varieties. Okay. So to get a morphism of varieties, what we need are two maps. So first of all, we have f mapping x to y, And this will be a collection of, this will be a map on the points of x, x1 through xn, and it will give me, and it will map to a collection of polynomial functions in these x variables, f1 through fm. Okay. This also gives me a map of rings. And it's going in the opposite direction. So I'm mapping from the coordinate ring of y to the coordinate ring of x. And this corresponds to a polynomial ring, a map from the polynomial ring in y variables to which is modulo some ideal defining y, mapping to the coordinate ring in x variables modulo some ideal j. And what it's going to do to any of these y variables is just send it to the corresponding polynomial function in the x variables that that defined the values of y in our original map. Okay. So it's a little weird that we're thinking about going first from x to y, and then in terms of the coordinate rings coming back from y to x, but the maps are actually defined in quite a natural way. So now we have morphisms of varieties. How do we get a family of varieties? So we're going to define a morphism from, and it'll be phi from x to b, where b is, we can think of this as a space of parameters. And the space x is going to be composed of variables and parameters. Okay. Then a given point b in B will correspond to a fiber phi inverse of B, which can be thought of as a variety corresponding in the space corresponding to variables. Okay, so an example will hopefully clarify this. So we can look at what if we want to think about the family of varieties defined by quadratic polynomials in two variables. So let's say the defining equation I'm interested in is a20 x squared plus a11 xy plus a02 y squared plus a10x plus a01y plus a00. Okay, so say I'm interested in varieties defined by equations of this type. Well, I could think about this as living in, so there are 1, 2, 3, 4, 5, 6 parameters, and then 2 variables. So I could view this as going from 8-dimensional space indexed by x, y, and the a variables, and mapping down to 6-dimensional space, just corresponding to a variables. And then each point in this K6 corresponding to a variables will define a variety upstairs in K8. Okay, so let's draw a picture of what's happening there. So K6 complicated space, which I'll represent by this blob. So let's say we have a point here corresponding to A20 and A02 are 1, and then A00 is -1, and then everything else is 0, then I can think about that coming upstairs from the following two-dimensional variety, or variety in two-dimensional space, being a circle. Okay. Meanwhile, but the fibers here are not particularly well behaved. I could take, for example, the point corresponding to all coordinates being 0, and then the corresponding function, the corresponding polynomial function, is just the 0 function, and so that means that everything is going to be to satisfy the polynomial equation trivially. So the corresponding variety is the whole plane. Okay. But at least we have a notion of what a family of variety means in terms of a morphism. Now we want to try and think about what a well-behaved family would be. Okay, so this one is not really well-behaved because on the one hand you have curves defined by degree 2 polynomial equations, but then you also have the whole plane. Okay, so there's nothing that's really consistent about that. Now let's think about hyperbolas. So here we have k. So we have this k3 corresponding to points x, y, a, mapping to k, just indexed by a. The reverse map would be just the injective map of polynomial rings k adjoin a into k adjoin x, y, a. And so what does this map look like? Well, let's draw the one-dimensional k, and let's consider what happens at various points. Okay, so pardon the sloppy cartoon. So we have, sitting above the point 1, we have the following hyperbola, xy equals 1. Okay, sitting above -1, we have a slightly different looking hyperbola. Right, now it's xy equals -1, so we're going to sit in different quadrants. What happens at xy equals 0? Well, there, what we're looking at is either x is 0 or y is 0. So we get this pair of lines. So on the one hand, the pair of lines is distinct from the hyperbolas we'll see on either side. On the other hand, it does really seem to belong. It's kind of a continuation of these hyperbolas coming in from the positive quadrants and then switching to the negative quadrants. So it does seem to really belong to this family. And this is characterized by the flatness property. So having families that are nice this corresponds to flatness in terms of what? Okay, well, in this case, so we're mapping x to b. So what we'll want is a of x will be flat as an a of b module. Okay, so whenever you have a homomorphism of rings, here we have a homomorphism of the coordinate ring of b into the coordinate ring of x. that induces a module structure on the target ring. It's an algebra structure, but also in particular a module structure. And having nice families of varieties, in the sense that you might intuit from this picture, corresponds to flatness of one coordinate ring over the other. Okay, and here's an example of a family that's not flat. So here, okay, we have k adjoin xt mod tx, the ideal generated by the product tx. This is not flat as a k adjoin t module. So what we're talking about here is a map from k2 to k. Okay, we have t parameterizing our varieties, and this is living in tx space. So we care about the equations defining the equations specifying x in terms of t as a parameter. So here's my t line. And then let's consider what happens at different fibers. So when t is 1, 0, -1, at t equals 1, then we're modding out by x. That's telling me x is equal to 0. Okay, so we have a line sitting above each of these, and the fiber of this map is the line where x is the point where x equals 0. And the same is true when we look over t equals -1, x is 0 still. And x is 0 no matter what non-zero t you specify. But when you specify t equals 0, obviously you're just modding out by 0, so you get this whole line. Okay, and this is similar to the space of quadratic curves defined by quadratic equations. There's something about this that doesn't sit nicely with the rest of this family. And indeed, k adjoin xt mod tx is not flat as a k adjoin t module. Okay, and you can see in particular that if I take the map k adjoin t to k adjoin t, and it's multiplying by t, this is an injective map. But then when I tensor with this ring, so let's say this is M, so k adjoin t, this is injective. But then k adjoin t tensor M, mapping to k adjoin t tensor M, is no longer injective. Let's put this in red. Okay. The reason being that when you apply this to one tensor x, this maps to 0. Okay. So what this whole discussion is about is an intuition for why flatness is an important property. Flatness seems to witness something about morphisms of algebraic varieties that correspond to particularly nice families, where every fiber of the morphism has a variety that seems to belong to all of the others. Okay, this is all very spiritual and not particularly precise, but the idea is to give you an intuition for why we might want this property, and leave the work to you as to really truly rigorously justify this in future courses. Okay, thank you very much.